Good day, everyone. My name is Katherine Develos Bagarinao. I'm a senior researcher at the Global Zero Emission Research Center at the National Institute of Advanced Industrial Science and Technology in Tsukuba, Japan. Towards the goal of achieving decarbonization and addressing the global demands for sustainable energy, at AIST, we are doing research on novel materials and electrochemical devices such as solid oxide fuel cells or SOFCs. For the development of materials for high-performance SOFCs, it is crucial that we utilize the appropriate tools to investigate fundamental properties and understand the mechanisms affecting performance. In this webinar, I will focus on the specific application of SIMS as utilized in our research in this area. Here is the outline of my presentation. First, I will present a brief introduction on the subject. Then I will discuss in detail three main topics. The first topic is on high-performance cathodes, where I will present our results on the development of nanostructured and multilayered thin film cathodes. The second topic is on interfacial properties, specifically oxide ion blocking effects as influenced by secondary phases formed at heterointerfaces. The last topic is modification of cathode interlayer interfaces for improving the stability and performance of SOFCs for long-term operation. Lastly, I will summarize the important points in this presentation. Solid oxide cells are highly efficient energy conversion devices, which comprise solid oxide fuel cells or SOFCs, which convert chemical energy into electrical energy via oxidation of a fuel, and solid oxide electrolysis cells, or SOECs, which are operated in the reverse process, wherein electrical energy is transformed into stored chemical energy. These cells are operated at relatively high temperatures, for example, 700 to 800 degrees Celsius, which makes the efficiency very high. In the illustration, hydrogen is used by the fuel cell to generate electricity, whereas in the electrolysis cell, electricity is used to split water to obtain hydrogen, which can be stored or used to produce synthetic fuels. Thus, the SOC technology is a very promising technology which can provide clean, reliable, and hopefully affordable energy in the future. The first topic I will discuss is about our studies on tuning cathode microstructure and orientation using model electrodes comprising thin film structures. Let us consider the SOFC mode in particular. This slide shows the schematic of a unit SOFC, where the fuel electrode or anode, electrolyte, and air electrode or cathode are the main components of the cell. The air electrode side is exposed to air, and this is where the oxygen gas molecules interact with the electrode surface and are consequently converted into oxide ions via several steps, collectively referred to as the oxygen reduction reaction. Afterwards, the oxide ions are transported through the electrolyte and then chemically react with the fuel at the anode side, here shown as hydrogen, to produce water and release electrons in the process. One way to significantly improve SOFC performance is to increase the rate of oxygen exchange processes which occur on cathode materials. There are many types of cathode materials, but the most common ones are perovskite-type oxides, such as lanthanum strontium cobalt oxide or lanthanum strontium cobalt iron oxide. These materials have very high surface exchange properties, which enable the fast incorporation of oxygen from the supplied air into the cell. Typical cathode materials are mixed ionic electronic conductors. This means that the oxygen reduction reaction that occurs on cathodes proceeds via a bulk pathway, wherein the oxygen atom receives an electron from the cathode and is then converted into an oxide ion and incorporated through the cathode bulk. or via the surface pathway, wherein the oxygen at atom diffuses across cathode surfaces, reaching the triple phase boundary, where it is then converted into an oxide ion. Here, the triple phase boundary is the region where the cathode, electrolyte, and gas phase converge. Conventional microstructures, on the other hand, are also comprised of microscale grains, typically prepared using wet processing methods like screen printing. This means that the density of triple phase boundaries is limited by the size of the grains. On the other hand, using thin film deposition, it is possible to tune the microstructures in the nanoscale level, which means that the grains can be grown with much smaller dimensions and possessing a much higher density of triple phase boundaries as well as grain boundaries. This is important because at the nanoscale level, it has also been demonstrated by previous studies that the grain boundary pathway provides a much faster route that significantly boosts the oxygen reduction reaction kinetics. This indicates that a viable strategy to improve performance is through nanostructuring. By improving the oxygen reduction reaction kinetics, it may also be possible to lower the operation temperature without any significant reduction in performance. To investigate the oxide ion transport through the cathode materials, we employ the isotope exchange depth profile method in conjunction with secondary ion mass spectrometry, or SIMS. This is a well-known technique that has been used to study a variety of bulk and thin film materials. Here, the sample to be investigated is isotopically exchanged by annealing in an enriched atmosphere containing the stable isotope of oxygen, 18O. The diffusion profile of the tracer gas is then obtained using SIMS depth profile analysis. This is the schematic illustration of the isotope exchange setup, and here is a photo of the SIMS machines used at AIST, namely 7F and 5F models. There are specific SIMS features which make it an attractive analytical method for SOFC research. First of all, depth profile analysis is possible with very high resolution in nanometer level. For devices like SOFCs, which are comprised of heterostructures of various thicknesses, being able to probe the layers from the surface down to the buried heterointerfaces allows us to extract important information, for example, about cation diffusion phenomena occurring across interfaces. Second, qualitative semi-quantitative analysis of elements below ppb concentration is possible. For SOFCs, the presence and accumulation of contaminants, for example, trace quantities of sulfur and chromium coming from the supplied air, is detrimental to their performance. Third, analysis of elements is possible using SIMS. Last but not least, isotope analysis is possible due to its high mass resolution. Therefore, in combination with the isotope exchange depth profiling technique, we can gain important insights into oxide ion behavior on surfaces as well as interfaces. This slide shows some of the results we have obtained in our investigation of various cathode structures. Here, we used a single crystal substrate, yttrium stabilized zirconia or YZ, with orientation of 100 and 111. On top of the YZ, using pulse laser deposition or PLD method, we also prepared a gadolinium-doped ceria, which is normally used as an interlayer when using YZ as electrolyte. This is to prevent the chemical reaction between the cathode, in this case LSCF, and the YZ electrolyte. We also varied the GDC microstructure by high temperature annealing. These are transmission electron microscopy or TEM images showing the cross-sectional microstructures of the different films, together with the selected area electron diffraction patterns and atomic force microscopy images obtained for each film. In particular, we were able to obtain three different types of LSCF, ranging from quasi-single crystalline with a dominant 100 orientation, mixed orientation of 100 and 110, and to a dominant 110 LSCF orientation. The main question is, how do the films behave in terms of oxygen surface exchange properties? To investigate this, we measured the amount of isotopic tracer that was incorporated into the samples as a way to evaluate the surface reactivity. These are typical SIMS depth profiles obtained for the three different samples. The plots shown as A, B, and C show the various elements comprising the different layers as a function of depth. The black line, in particular, refers to the 18O oxygen isotope, which you may recall was used as a tracer for the experiment. In the plot shown in D, we can see that the film having a dominant 110 orientation, shown in green, shows the highest concentration of 18O incorporated into the YZ electrolyte. From a fitting of the 18O profile using the crank solution to the diffusion equation shown on the right, we can then obtain the oxygen surface exchange coefficient, denoted as K star, as well as the diffusion coefficient, denoted as D star. What we found out is that the apparent K star is much higher for the thin film samples compared to typical LSCF bulk. And it is higher by at least one order of magnitude for the film with dominantly 110 orientation compared to the film with dominantly 100 orientation. This drastic improvement is attributed to the comparatively higher catalytic activity of the 110 surface. Another approach we explored is the multilayered structure prepared by alternately growing two different types of thin films. The figure on the left shows a typical cross-sectional TEM image of a lanthanum strontium cobalt oxide, or LSC, and gadolinium-doped ceria, or GDC, in a multilayer composed of two pairs of each film. Each layer is characterized by nanocolumnar grains and appear uniformly stacked on top of each other with clear, well-defined interfaces. To further probe the electronic structure of the samples, we also performed spatially resolved STEM electron energy loss spectroscopy, or EELS measurements on the multilayers. On the right is a typical EELS spectra depicting the L3 and L2 edges for cobalt, M5 and M4 edges for lanthanum, and M5 and M4 edges for cerium. In particular, we were interested in looking at the changes of the cerium peaks. The ratio of the intensities of the M5 and M4 peaks provide information on the valence state of cerium, meaning we can get some quantitative information of how the valence state of cerium changes from 4+ to 3+ across the LSC-GDC interfaces. We obtained the EELS spectra from various LSC-GDC interfaces and calculated the M5-M4 ratio as shown in this slide. Here, we can see that the M5-M4 ratio is well below 1 throughout the GDC region, implying that the cerium valence state within the GDC film is most likely cerium 4+. However, there appears to be an increasing trend at the GDC-LSC interface, where the M5-M4 ratio being higher than 1 indicates the presence of cerium 3+. Interestingly, this result suggests that there is a tendency for the existence of reduced cerium near the vicinity of the interface with the LSC layer. The presence of cerium 3+, on the other hand, suggests the existence of oxygen vacancies along such interfaces, which can be considered as active sites for oxygen incorporation. This slide shows the comparison of the SIMS line scan profiles across cross-sections of samples with single-layer LSC cathodes in comparison with LSC GDC multilayers. You can see the differences in the relative amount of the 18O tracer between the single layer in comparison with the multilayer. From the fitting of the SIMS profiles, we extracted the apparent surface exchange coefficient, or K star. We found an improvement in K star for the multilayers by almost 1 order of magnitude. The next topic is about the process of transporting oxide ions across heterointerfaces. Ionic transport can be strongly affected by factors such as poor contact, defects, or secondary phases, which arise from cation interdiffusion between adjacent layers. One way to mitigate the formation of secondary phases is to utilize a barrier layer or interlayer to block the cation interdiffusion. Nevertheless, this does not present a 100% solution, and depending on the type and condition of the interlayer utilized at such interfaces, the formation of secondary phases still remains as a major cause of long-term degradation and decreased performance in SOFCs. A prime example of secondary phase formation in typical SOFCs is strontium zirconate. This arises from the chemical reaction between a common cathode material, LSCF, and YZ, a state-of-the-art electrolyte. Here, gadolinium-doped ceria, or GDC, is utilized as a barrier layer between LSCF and YZ. The SEM-EDX images on the left-hand side show the cross-section of the diffusion triplet, which was annealed at 1200 degrees Celsius for 168 hours. Here, we can see the formation of strontium zirconate on either side of the dense GDC layer, indicating that strontium from LSCF and zirconium from YZ have mutually diffused across the dense GDC layer and reacted to form strontium zirconate. On the right-hand side is another related study which showed that after cell tests, strontium zirconate formed at the LSCF GDC interface as a result of extensive zirconium migration in the PLD-grown GDC interlayers. The lateral growth of strontium zirconate along the LSCF GDC interface is accompanied by a remarkable increase in the polarization resistance with operation time, especially under open circuit voltage condition. It is therefore clear that the strontium zirconate formation drives the rapid degradation of the cell performance with time. Towards a better understanding of the role of interfaces in general, as well as to elucidate the influence of secondary phases on oxide ion transport, one approach we have adopted is to use model systems based on thin film structures. To understand the effect of strontium zirconate in particular, we prepared heterostructures where the strontium zirconate or yttrium-doped strontium zirconate layers are sandwiched in between GDC and YZ, similar to the commonly observed structures of sintered SOFC cells. The slide shows some representative AFM images and XRD patterns showing the multilayers of GDC and strontium zirconate prepared on YZ. The films are highly crystalline and have dominant orientations, which are influenced by the YZ single crystal substrate orientation. This slide shows typical cross-sectional TEM images obtained for the two types of heterostructures. This shows the SIMS depth profiles of the samples isotopically exchanged at 600 degrees Celsius for 5 minutes. The individual elements comprising each layer are shown as plateaus in the depth profile, and the boundaries or interfaces between layers can be seen as sharp drops in the profile. To illustrate this point, for the plot on the left, we can see the gadolinium and cerium signals as plateaus in the GDC region. And at the interface with the strontium zirconate layer, we can observe that these signals exhibit a drastic drop, simultaneous with an increase in the strontium and zirconium signals, indicating the onset of the strontium zirconate region. In addition, we see that the yttrium signal shows a broadening from the YSU region into the strontium zirconate region, indicating that the yttrium has diffused. This suggests that in the vicinity of the strontium zirconate interface, there is some amount of yttrium in the composition of the material. On the other hand, the concentration of the 18O tracer normalized using the equation shown is plotted as black curves in the plots. What is interesting about the 18O plot is the fact that whereas they show a rather high concentration in the GDC region, indicating very fast diffusion, they exhibit sharp drops at the interfaces with strontium zirconate or yttrium-doped strontium zirconate. This indicates that the oxide ion transport is significantly blocked at such interfaces, which suggests the existence of oxide ion blocking effects. These results therefore indicate that the degradation and cell performance can be associated with the blocking of ionic flow at such interfaces. Next, I will discuss some results on the modification of interfaces to improve stability and cell performance. As we have seen, the formation of the strontium zirconate at interfaces is one of the major issues concerning the long-term stability of SOFCs. Here, with the aim of controlling the interdiffusion phenomenon and thereby reducing the strontium zirconate formation, the last topic deals about the modification of the interface via a dense LSCF layer in addition to the dense GDC barrier layer prepared using PLD as a means to control the mass transport across the cathode and interlayer. For this experiment, we utilized a polycrystal YZ substrate upon which a dense GDC interlayer was prepared using PLD. In addition, a dense LSCF layer of approximately 300 nanometers was subsequently deposited. Porous LSCF was then screen printed and co-fired at 1080 degrees Celsius. The electrochemical tests were carried out at 800 degrees Celsius up to a total of 300 hours in both open circuit voltage and polarization. The slide shows the comparison of the polarization resistance for the two types of samples. We can see that the polarization resistance increases quite rapidly for the sample without dense LSCF, but shows relatively low and stable values up to 300 hours for the sample with dense LSCF. From these results, we can conclude that the degradation of the polarization resistance is greatly reduced by inserting a dense LSCF film, which improved the cell stability. Further analysis using SIMS were carried out to gain information about the diffusion of strontium, zirconium, including cobalt and iron across the GDC interlayer. Here, we removed the LSCF cathode and performed depth profile analysis across the GDC layer and YZ electrolyte. Shown on the left are the normalized SIMS profiles for the various elements. Here we can see the evidence of extensive diffusion of strontium and zirconium across the GDC interlayer without the LSCF dense layer. In contrast, these are significantly decreased for the case of the sample with the dense LSCF layer. We also find that the extent of cobalt and iron diffusion, evidenced by the presence of a peak at the GDC-YZ interface, are also similarly reduced. In other words, by improving the stability of the LSCF-GDC interface, we were able to consequently mitigate the strontium zirconate formation and improve the long-term stability of the cell. To summarize, in this presentation, I have discussed 3 specific topics concerning the development of materials for SOFCs. The first topic is on non-structured and multilayered cathodes, exhibiting superior surface exchange rates compared to conventional materials. The second is on the oxide blocking effects due to the strontium zirconate formation. Using the model structures and employing SIMS isotope labeling technique, we were able to confirm the role of the strontium zirconate layer on oxide ion transport across such interfaces. The important finding is that it is not the strontium zirconate layer per se that blocks ionic flow, but the nature of the interfaces with this phase. Lastly, with the goal of mitigating the effect of strontium zirconate on long-term degradation, we devised a way to improve the stability of the interfaces via introduction of an additional dense LSCF layer, which in conjunction with a dense GDC layer, helped to further reduce cation interdiffusion in the cell. With this modification, we were able to improve the degradation rate with long-term testing and achieve better stability of the polarization resistance with time. For each of these investigations, I hope I have shown that SIMS as an analytical tool plays a major role in our development of materials for high-performance SOFCs. With this, I would like to end my presentation. Thank you very much for listening.